In this video, we will take a look at how running programs, programs that are running on Linux, how they see memory. So we will take a look at 32-bit Linux processes, mainly because they have a nice compact address space. It's a huge amount of memory. It's a 4 GB chunk of memory, but these memory addresses are a little bit more manageable than 64-bit systems where it's a lot bigger and a little bit harder to understand just because of the lengths of the pointers. Okay, so we're going to deal with 32-bit Linux systems. Each program views memory as a single 4 GB chunk of memory. So you don't have all 4 GB of memory, of course, because if you had that, then if you had two programs that are running, they would each need 4 GB. That means 8 GB. And if you look at most systems, they will have many programs running. So let's just take a quick look using top. And here there's a total of 143 programs running. Each of these programs see memory as a 4 GB chunk. So that would, if they all had separate 4 GB of memory, that would mean something like 500 and some gigabytes. Of course, we don't have that much memory. If you look at the total memory, this is a live DVD. It has 1.5 gigs of memory. No swap space, that is no hard drive space that's used to store contents of RAM temporarily. So, okay, so that's top. From top, we can tell a lot. It also tells us, well, even though each program sees memory as a 4 GB chunk, they don't use all of it. Every program doesn't use 4 GB, so that's really why you don't need that much memory. Each program uses just a tiny amount of memory. Just Linux is pretty efficient. So depending on your system, you might see different numbers. If you do this, if you cat this command, if you execute this command, cat /proc/meminfo, it'll tell you information about your memory on your system. On this system, it has half a gig of memory plus some swap space. This is an old system. It has 1 gig of swap, so that overlaps with this memory. It's a total amount of memory really is 1 GB. And most systems these days don't even have to use swap. They do have it, but you almost never even use swap because most systems memory is so cheap right now that the simplest system these days will have 4 GB of memory. You'll never use all of that. Okay, so but on older systems we need to. Large servers every once in a while will go past their DRAM limit. That is, if you have a DRAM that is actual memory chips that add up to, let's say, 4 GB. Well, actually, servers these days will have much more than that, 32, 64, 128 gigabytes. But if you hit a busy period where you need a lot of memory, yeah, you might end up using the swap. It's always good to have, although I realize most of you probably will never use your swap space at all. So how are you able to set up a program or run a program which sees memory as 4 GB chunks, as a single 4 GB chunk, but only have, let's say, 512 megabytes or half a gig of DRAM? Well, what happens is the Linux virtual memory system plus the CPU takes care of pretending like each process has a 4 GB chunk of memory. You don't have to think about it. The virtual memory system deal with all the things that you need to do so that it seems like you have this 4 GB chunk. Okay, so every program is set up that way. The C compiler sets up, puts everything in just the right places, and the loader loads your executable file in such a way that you use certain areas of memory. Stack is in a fixed place, your program is loaded in a fixed place inside this 4 GB chunk, your heap is in a fixed place, you can access parts of it, but it starts at a certain fixed location. So the CPU and the OS use DRAM and swap space on a hard disk to give each process the illusion that there's more memory than there actually is. So it uses swap as a backup. Okay, so no matter how much memory you have. So it's true on older systems that you definitely need a swap space. These days, memory is cheap. You have large amounts of memory. You may never touch the swap unless you're running some massive programs. So it's still possible. So at any time, only parts of a process are actually used and loaded into DRAM. The rest of it is on disk. Sometimes it's not even loaded, sometimes it's on swap. And these are actually, if you were to look at the actual sizes, each individual chunk is only about 4 kilobytes of memory. And that can be anywhere in DRAM. It might be these lower values, these chunks at lower addresses might actually be a completely different address in the actual physical RAM. You don't have to worry about all this because our Linux operating system kernel takes care of how they actually map to physical memory. So if each process can use 4 gigabytes, how can all the processes on a system use the one, let's say in this case, half a gig of DRAM plus swap space of 1 gigabyte? That's a total, actually that's part of this is in swap. So total of 1 gigabyte memory available. Well, how does it do that? The key is that most processes use only a small part of the 4 gigabytes available to them. So your program is always loaded to this area of memory, 0x0800 something something 0000. That's text, that's called text. That's your machine instructions that constitute your program, your executable file. This has read permissions only. The stack is initialized to start at BFFF, FFFF, and grows towards smaller addresses. And it's usually stacks are limited to about 8 megabytes, although I haven't actually looked at the limits recently. Usually stacks are limited in size so that once you hit that limit, you say, all right, there's something wrong. You shouldn't need 8 megabytes of memory, so chances are you have something like runaway recursion or some kind of problem. Okay. We will take a look at how a program like this is loaded into memory. So remember, all of this program, all of this stuff is compiled into machine code and loaded into the text area of memory. The stack we will be using because, for example, this str variable, although it's an array of characters, that str variable is on the stack, and it turns out this sequence of letters, this string is actually stored in the stack as well, and we will see that when we run our program. When we call print length, we will use the stack because every time you use a function, we put things on the stack, and so this pointer, the place where this is stored is on the stack. It will point to some area of memory, which in this case is also the stack. N is on the stack. This constant, this is actually a string constant, which is probably going to be near here in a small section called the data section. Alright, so we will find out. And then what we will do is we will take a look at a simple program and use the debugger to see where addresses are. So let's take a quick look at this. Alright. Here's all our C files. Let's create an executable. gcc -o main. Oops. We need the -g flag. Main.c, length.c, println.c. Alright, gdb main. Oops, gdb main. There we are. List. Let's break at 10 and run. There we are. And let's see what we have so far. Okay, so here we have, let's print str1. It doesn't really tell us where str1 points to, but it is it shows us what the string is. And then let's print str2. Luckily, this shows us where the string points to and the contents. So here's the contents of memory of that string, and here is where it points to. This looks like it is somewhere near that text area, and what we'll see is that it is actually in the heap. So the heap is pretty close to here. So there's a whole bunch of things here. This is not actually drawn to scale. The heap is 0x08 something. The exact value we can't really, you could tell, but due to things like stack randomization and heap randomization, probably heaps are actually pretty random. These values will change ever so slightly, just so that things like viruses and worms can't take advantage of things being in the same spot every time. Okay. So my guess, although it's not completely certain, my guess is this is on the heap somewhere. So here we are with str1, str2. We saw that they're in different places. Well, let's take a look at, if we step into this print length function, we can see what str is. So let's do a step. Right now we are at line 10. If we take a step, there it is. We can see that s, which is str1, has the value 0xbfff f36a, which, as we saw, is pretty close to the stack. So this tells us that str1 is pointing to some area of memory on the stack itself. Okay. So, and all this function does, we can list it, we see that it only has one line of code. You can step over it. It prints this length of string is 17. All of that worked. Let's go next. Let's step into here. Here we see something different. str2 is 080486A0, and that we know is somewhere close to here. My guess it's coming from the heap. So those are the kinds of addresses you want to recognize. Those two kinds of addresses. If you see something like 0xbfff and then ff or f36a, you know that's a stack address. If you see something like 08, the leading 0 might not be present. If you see 80486A0, you know that's a heap address. So that's the kind of thing you want to be able to tell just by looking at some of the addresses. You don't have to remember these things for a quiz or anything, but recognize these addresses. You can be able to tell what's on the heap versus the stack. That's a very useful thing to know. So you don't have to memorize this, but make sure you understand what this picture is telling you about Linux processes.